All right, guys, lesson 10.2 is all about vectors. So this is going to be kind of like a pre-calculus lesson, similar to the one that we did over three-dimensional systems, coordinate systems, because you are expected in calculus to use vectors, not really in the manner that we're going to discuss today. However, I wanted you to have a little bit of understanding behind vectors before we get into the calculus application of them. So if you've had physics before, this is going to be review. If not, this is still pretty simple stuff. So the idea is a vector kind of looks like a ray in geometry, and vectors are used in science to indicate something that has magnitude and direction, meaning the size of the vector or the ray that's drawn and the angle in which it's drawn is significant. They represent something. So the arrow, you got to pay attention also to where the arrow is pointing. That also designates the direction of the vector. Notation-wise, vectors are written with typically the letter V, sometimes the letter U. And we write them in boldface. So like you write the letter V, but you kind of make it even more bold when you're describing a vector. But what you can also do, if that's not real feasible to do, is you can do V with a little arrow above it, and that also means vector. Okay, so let's talk about vectors. So let's pretend we have two vectors. Vector AB is this one here, and vector BC. And you'll notice that they're both pointing in opposite directions. So what they're doing is these vectors are representing a particle movement. So it says in this problem, suppose a particle moves from A to B. So its displacement, distance traveled, vector is AB. Then the particle changes direction and moves from B to C with displacement vector BC, as in figure 2. The combined effect of these displacements is that the particle has moved from A to C. So what that means basically is the AC vector would be like total distance traveled from the beginning to the end of that particle's movement. Okay, so we use vector AC to designate the sum, like I said, distance traveled, but also the sum of the two vectors. Okay, so first thing we're going to do is we're going to look at how to draw vectors, vector addition. And there's two ways to do that. I think this parallelogram law is kind of silly, so I'm going to go over here and look at the triangle law. So if you are tasked with taking vectors and adding them together to create the vector sum, what you'll do is you'll take the first vector, in this case U, and you will not change its angle, you will not change its size, you will just draw it on your paper. And then you will take vector V and you will put the initial side against the terminal side of vector U. So the beginning against the arrow, against the ending of the other vector, and you will, again, not change its size and not change its direction, but you're just going to slide it over and put it right on top. And then wherever the beginning of vector U to the ending of vector V, you will draw a line to connect the two, and that will represent your vector sum. So let me show you what I mean here. Keep in mind, I'm drawing on an airliner, so this might not be super accurate, but I want to draw vector A, the sum of vector A and vector B. So my attempt is going to be to recreate the exact angle and size of vector A. That's fairly decent. And then I'm going to take vector B and I'm going to line it up with the ending, the terminal side of vector A. And I'm going to try to keep it the same exact angle as shown in this picture here. But I'm just putting the beginning up to the end of vector A. And then I'm going to connect basically from the beginning of A to the ending of B. And it goes in that order, by the way. The beginning of A to the ending of B. So I'm going to start over here, and I'm going to go this way. And that vector that I just created would be called the vector sum of vectors A and B. Okay, you can take vectors and you can multiply them by constant values. And what that will do is that will change the magnitude, the size of your vector. Okay, so let's say I start with vector v and it's about this length. 2 times that is just going to be double the length. Half of that would be half the length. Okay, so hopefully those are pretty straightforward and make sense to you. Negative multipliers change the direction. So instead of going up, it's just going to go in the opposite direction, like 180 degrees from where it currently is. And same thing over here, but this one would change the size and we would change the direction because it's negative and it's a constant multiplier. Okay. Subtraction. So when we are looking at differences between vectors, what we're going to be doing is we're going to be thinking of this as addition. Okay, so all of you should know by now that when you are subtracting something, it's the same as adding a negative. And so that's how we're going to figure out the diagram for subtracting vectors. We're going to think of it as taking vector u and adding the negative vector v. Okay, so as we saw in the last slide, if you take a vector and you make it negative, that means it changes direction. Okay, so if right here is vector v pointing upward, then negative v would be pointing downward. All right, so we are going to make that change to show how to subtract vectors. So you'll take vector v, you will switch its direction, and then you'll line it up just as we have been doing, vector u and then negative v. In this diagram, I took negative v and slid it down or slid it over so that it would hit the tail end of u. And then this blue line in the center would then show the difference between u and v. Okay, so let's try an example. We're going to take, it says do a minus 2b. So according to the directions, a minus 2b is what we're asked to draw, but that would be the same as a plus negative 2b. So let's get a drawn first. So let's draw a. Remember, you don't change the size or the direction. So it's the same size, same direction as what's shown. But then for b, we have b, but we want negative 2 times b. So we want the size of vector b to double in length, and we want it to go the opposite direction to make it negative. So I'm going to try to do that from here. I'm going to it to be twice the size. Maybe we'll look like that, and it's going to face the opposite direction. And I went ahead and lined it up so that the beginning of this vector is at the end of vector a. And then we can make our difference vector. And so that means we go to the beginning of a all the way to the ending, and that would be a minus 2b. That would be the vector that represents a minus 2b.